Section 17.3 is electric field. We're going to have two objectives here. We're going to first calculate the strength of an electric field, and second, understand how to draw an electric field line. So to start, let's talk about the definition of what an electric field really is. And it's a region where an electric force could be felt on a random test charge. And by test charge, it just means if you were to put a positive charged particle somewhere in space, would it feel a push or a pull? If it does feel a push or a pull, it means it's in the field or in the range of some electric field. So there must be some field producing that. So if there's a positive field existing somewhere, and you bring a positive charge toward it, it's going to be pushed away. It's going to feel that. So we would say the electric field would be to the right here. And here, imagine there's like a negative region. If you bring a positive point charge or a test charge here, it's going to feel a pull to the left. So what we can do is we can define our electric field intensity really, or electric field strength, as the force over the point charge itself. But if you remember from the last section, force is defined as Kc Q1 Q2 over R squared. Well, one of these charges, right, this is Q1 maybe, and this is Q2. This Q2 is really the point charge, right? This is the test charge. So that test charge is there, but it's also here. So these test charges cancel each other out. When these two values cancel out, you get Kc Q over R squared. Similar to the formula we had for electric force. So for electric field lines, to draw them, just think of the direction that the force would act from a field producing charge on the test charge itself. So, for example, a test charge would be pushed away from a positive source and it would be pulled away from a negative, or pulled toward a negative source. Positive charge, positive source, it's going to push it away. Positive charge out here with the negative source, it's going to pull it inward. So keep that in mind when you're going through your drawings of fields. Some general rules for field lines. First, field lines can begin on positive charges or at infinity, and they must end at negative charges or at infinity. The number of field lines from a charge is proportional to the magnitude of the charge, so the more lines that come out, the more dense the lines are next to each other, the stronger the field is on a diagram. And third, field lines from the same field cannot cross, like contours, okay? Like contours. So let's take a look at some sample fields here. On the left here, we're going to see the field that would exist between a positive and negative point charge. And again, notice that the field lines originate either at the positive charge, right, and they go to the negative, or they originate out at point away in infinity, at a point infinite distance from the negative charge, and they come in, but they always end at the negative charge. Again, going away, though, from the positive charge, going away to infinity or away to a negative. This is coming in from infinity or coming in from a positive. Two positive point charges near each other obviously will repel. So these field lines here, right? These field lines would move up, and these field lines would move up, and they'd repel each other. So these would all move away to infinity. And these field lines here will run along one another. Finally, a field that's drawn with a positive charge that's twice the magnitude of a negative charge, take a look at its direction and its field. So we're going to see that these lines are much stronger. This charge here is much stronger. So some of these field lines are looping in here into this negative field, but a lot of them are getting away in this positive field. Okay, going toward infinity, this negative charge being a little bit weaker than the positive charge here. So example 1 says a charge Q equals 10 microcoulombs produces an electric field. Determine the electric field at a point 10 centimeters from the charge. Then determine the electric force felt by an electron at this distance. Will this force be attractive or repulsive? So first let's start by listing what we know. We know the value of Q, and that's 10 microcoulombs, so times 10 to the negative 6 coulombs. We also know that the distance from that charge is 10 centimeters or 0.1 meters. And we're trying to determine the electric field at this point. So we start by saying, well, electric field, remember, is Kc Q over R. So all we need to do is plug in, remembering that Kc is 9 times 10 to the 9th Newton meters squared per coulomb squared. So plugging in these numbers here, again, plugging in Kc, plugging in Q, plugging in the R, for the electric field, we're going to end up getting here a value of 9 times 10 to the 6th, and notice my units are newtons per coulomb. Now next we have to let Q0 be equal to the charge of an electron. That was the question. It said, then determine the electric force that would be felt by an electron at this distance, not by just some random point charge anymore. So what would the force on an electron be? Well, we can go through this whole thing again with Fe and use our force formula between an electron and another charge, or we can just simply go back and think to ourselves, well, we had a formula earlier that said the following. We started with this. The electric field is equal to the electric force over the point charge here. So if we let Q0 be equal to that charge on an electron, we could figure out what Fe is by multiplying by Q0, right? Let's bring this Q0 up here. Q0 times E is equal to the force felt on an electron. Well, we have E value. We have E from up here, so we'll plug that in right there for the electric field. For Q0, plug in the charge on an electron. Charge on an electron, 1.6 times 10 to the negative 19 coulombs. This is negative. And why is this negative? Because it indeed is an electron. And then we have this field here, 9 times 10 to the 6 newtons per coulomb. So multiplying these two is going to give us a value of negative 1.44 times 10 to the negative 12 newtons. Very small force felt. Okay, but notice the negative sign, okay, since again it's the negative sign, we're going to know that this is going to be an attractive force, okay? Since the charge produced in the field is positive and this is an electron and an electron is negative, they have to attract. Again, coming from the negative sign here, seeing that we have a negative here. Remember, with electric field or electric forces, the negative sign indicates that they're attractive. Example 2 says, determine the electric field produced by two charges of 3 times 10 to the negative 8 coulombs and negative 2 times 10 to the negative 8 coulombs at a point that is halfway in between them. So now we're going to take a look at a point halfway in between these two charges. And we're saying that they're separated by a distance of 40 centimeters. So what's happening here is that we have Q1 that's going to produce its own field. And that charge is 3 times 10 to the negative 8 coulombs. Then we've got this Q2 that's going to produce its own field. Negative 2 times 10 to the negative 8 coulombs. So we're going to have fields that are going to act against one another, clearly, because they're opposite charges. Next, we want to find out what the field is halfway between them, so we know that the R value away from each of these is going to be 20 centimeters, or 0.2 meters. Each one of these has the same R value, 0.2 meters. So what we're going to do is we're going to calculate the electric field for the first one with Kc, Q, and we'll call that Q1 really, over R squared, and the electric field in the second case from the second charge of KCQ2 over R squared. And again, knowing that Kc is 9 times 10 to the 9th newtons meters squared per coulomb squared, what we end up getting for these is 6,750, and that's again in newtons per coulomb. And in this case, we get negative 4,500 newtons per coulomb. So we're looking at a point in space halfway in between these 2 points, so what we can do is use the principle of superposition.